Hey A&P students, time for lecture number 2 on bone tissue. That's right, lecture number 2 on bone tissue. Hopefully you got through number 1 and all that information is sitting snugly in your brain. Time for number 2. So what we are looking at here is something that is familiar from lab. We're looking at some compact bone, all right? And we are seeing the basic structural unit of compact bone. I'm going to draw a big old circle, big red circle, not a perfect circle. Who can draw a perfect circle anyway? So big old circle right there. That structure within that red circle is, of course, known as an osteon. This is one of the major support structures we find in compact bone. And recall from lab that in the middle of that osteon there is a passageway for blood vessels and nerves. Because it is in the middle of the osteon, it is central. It's a passageway, so it is the central canal. And then, extending circularly around that central canal, we have these layers of bone matrix, layers of collagen, layers of hydroxyapatite, which you know is calcium phosphate and calcium hydroxide. Each of these rings of matrix, of course, is a concentric lamella. Concentric because they are sharing the same center. There we go. Now what else do we see here in this osteon? We see little cavities. Here is a little beautiful cavity right there. That, of course, is a lacuna. A lacuna. Lacunas are the residences of osteocytes, the cells that persist within bone matrix and modify it and make sure it is always okay. Of course, remember, osteocytes were once osteoblasts, the makers of the bone matrix. One other thing I can see here, interconnecting the lacunae, I see all of these beautiful little canaliculi. There is one canaliculus right there. Another canaliculus right there. There are so many. That's a really nice dark one right there. So many canaliculi linking the lacunae, which allows the osteocytes to communicate. Remember, osteocytes are surrounded by bone matrix, which is hard and dense and is not going to allow diffusion through it. So things are able to travel from cell to cell by way of the canaliculi. All right, this is a basic functional structural part of compact bone. Okay, let's look at some more figures of this. Let's clear that out. Here we see a drawing of an osteon. We are looking at the microscopic structure of a long bone, by the way, if we're looking at an osteon. Here we see the central canal of an osteon. We see a vein and an artery and a nerve going through there. Then we see 3 layers of bone matrix, each with the central canal as its center. Hence they are concentric lamellae. And I see some osteocytes residing in their lacunae with their extensions going through canaliculi. Look at another view of the same thing, a little cutaway. We can see all these things beautifully again. Pair of blood vessels and a nerve in the central canal. 1, 2, 3, 4 concentric lamellae. An osteocyte in its lacuna, another one right there. Extensions going towards one another by means of canaliculi. And it allows the osteocytes, which of course have gap junctions, to connect their neighbors, to exchange nutrients, wastes, gases, information. One of the things we'll find out about osteocytes is that they are constantly measuring the stresses put on bone, so they can then talk to the osteoclasts, who break the bone down, and talk to the osteoblasts, who build the bone up. All right, this is our basic basic osteon. Now we're going to put some osteons together. So I got an osteon right here. I got one right here. Another one. I got a whole bunch of osteons here. Look how they extend the length of this long bone. Osteons make up the shaft, the diaphysis. Remember that word diaphysis? The shaft of my long bone is called a diaphysis. So basically from like right here to right here, that is my diaphysis. And it is made primarily of osteons. And don't forget, from lab, we do have some other lamellae going around the entire outside. Those other lamellae are the circumferential lamellae. And of course, they are surrounded by the periosteum. So, this is a little review from lab, a little review of long bone structure. Oh yeah, by the way, before I go on, I'm so anxious to get going here. Don't forget about the perforating canals, which are going to link central canals together. By the way, bone has to have holes in the shaft. There have to be holes in the side here to allow blood vessels to even get in the first place. A hole in the side like that is called a nutrient foramen. Foramen because it's a hole. We met that word in lab this week. And nutrient because we're going to have blood vessels coming in. And of course, blood vessels, what are they supplying? Well, nutrients. All right, guys. Let's clear that. Let's keep going. Look at this. I want you to pause this. I want you to point out some osteons, some central canals, some lacunae, some canaliculi, some concentric lamellae. So those osteons, central canals, concentric lamellae, lacunae, and canaliculi. Point out those 5 things. Pause it if need be. Okay, here we go. Another picture. We're zooming in on an osteon on the left-hand side. I want you to shout out right now what A and B and C and D all are. If you can figure out B, then that is really good. Okay, long bone structure done. Flat bone structure time. And this is something we covered in lab as well. Look right over here. We got that parietal bone right there. We're zooming in on that parietal bone. There it is. And on that parietal bone, notice my sandwich. Compact bone is the bread. All the filling of the sandwich right in here. Spongy bone. We see that spongy bone down here. The spongy bone in the flat bone sandwich is better known as the diploa. Diploa. Don't forget that umlaut right there on that E. Of course, if we zoom in on the spongy bone, we see its lovely trabeculae, these interconnecting struts of bone. We see spaces in between them. The spaces are going to be occupied by what I see over here, which is red bone marrow. And of course, red bone marrow, what does it do? Quick answer is hematopoiesis, which is the synthesis of blood cells. Right. Excellent. Flat bone structure. That slide is done. Now we are going to talk about how long bones grow longer. So remember, long bones. Got them in our appendages. Pretty much all our appendicular bones, or our limb bones, let's say that. Pretty much all our limb bones except for our carpals, tarsals, and patelli, are long bones. Long bones have got to grow longer. In order for long bones to grow longer, we have to have this blue thing right here. We've seen this blue thing right here. This blue guy right here is an epiphyseal, because it's in the epiphysis. It's epiphyseal. It's an epiphyseal plate. You can't have long bone length growth without an epiphyseal plate. And by the way, this growth in length I'm going to be discussing is called interstitial growth. That's the term for it. Okay. Remember for me, the epiphyseal plate is made out of hyaline cartilage. It's made out of hyaline cartilage. I just put the T right there. That says cartilage. Cartilage. Should be cartilage. My bad. So this is hyaline cartilage right here. All right. Now, what is going to happen is this cartilage is going to change in two ways. The cartilage on the side closer to the epiphysis is going to grow. Okay? That is going to push the epiphysis up. That is going to make the bone grow longer. But, there's always a but. We don't want the plate itself to get bigger. We don't want more cartilage in the bone. We want more bone in the bone. So we grow the cartilage on one side, the epiphysis side. But then on the other side, the diaphysis side, the cartilage that's here is going to turn into bone. So we've done two things. We grew cartilage, which made the bone get longer, and then on the other side of the plate, we turn cartilage into the bone, and that makes sure we don't have just more and more cartilage. And notice the epiphyseal plate is still there. It still exists. It has not gone anywhere. And because if it disappears, well, then growth is done. So, epiphyseal plate, long bone growth. Epiphysis side, we make more cartilage. Diaphysis side, we turn cartilage into bone. And voila, the bone is longer and the plate is still there. Beautiful. Let's expand on this a little bit more. There we go. If we zoom in on the plate, so this is the epiphyseal plate we're zooming in on right here. Okay. This is up here, this is where the epiphysis is going to be. On this side, the diaphysis is going to be down here. So on the epiphyseal side, we have this region called the proliferation zone because that is where cartilage is growing. Notice it says cartilage cells are undergoing mitosis. They're dividing. Underneath that, we're going to see a transition. So cartilage cells get bigger. It's called the hypertrophic zone. More trophic growth. Then we start to see a change. The cartilage matrix starts to become calcified. Well, what are we doing here? If we're getting calcium in there, we're turning into bone. Cartilage cells start to die. The cartilage matrix starts to deteriorate. And then at the bottom here, the diaphysis side in this picture, this is the ossification zone. This is where we're actually making new bone matrix itself. So if we zoom in, we can see the process closer up. Remember, same thing happening. Epiphysis side, cartilage growing. Diaphysis side, cartilage is turning into bone. So proliferation zone, cartilage cells are growing, pushing the epiphysis up. That's growth. Then the other three zones, hypertrophic, calcification, and ossification, that is showing us how we are turning it into bone. which is what we gotta do. Yeah. All right. This is good stuff. I know you're enjoying this stuff. Who's enjoying it more, though? Seriously, me or you? Who's enjoying this video more, me or you? The answer, of course, is me. It's definitely me, no doubt. You ever been in a class where you like it more than the teacher? That is a bad situation. If you're having more fun than the teacher, if the teacher hates to be there. If you're in a class like that right now, I don't know if you can get out of it or not. Might be too late. Anyway, what am I doing? I'm wasting time here. I don't want to waste time. You don't want to waste time. Let's keep going. Yeah, this is a slide of a child's bone here, which is always kind of sad when you think about you're looking at the slide of a child's bone, right? Think about that for a second. What do we got here? We got the epiphyseal plate. Look at that beautiful thing right there. This is the epiphyseal side. This is the diaphyseal side. You should be able to tell me what is happening at each end. So pause it, shout it out. If there is a person near you, tell them, say, hey, come here. I want to tell you something. And let them know what's happening. All right? And don't forget about the zones. Don't forget about the zones, okay? The proliferation zone, the hypertrophic zone, the calcification zone, the ossification zone, PHCO, PHCO. All right, guys, zooming on along. Well, what is going to prompt growth to occur? What is going to make bone growth occur? All right, when you're a kid, there is, oh no, I switched slides. When you're a kid, there is a hormone that's going to be super important for this interstitial growth. It is called growth hormone, appropriately. Growth hormone is made by a little gland hanging off your brain. It's made by the anterior half of the pituitary gland, which is right there. So that is the pituitary gland. The anterior half of it makes growth hormone. Pituitary gland. All right, do me a favor. Send me an email. Tell me the bony structure and the bone that holds the pituitary gland. And I will give you a whopping 1 point extra credit. That's how I know how people are watching these videos, too. If you send me this in a timely fashion, I know you are on the ball. All right, pituitary gland, making growth hormone. Growth hormone is going to act on the epiphyseal plate. It acts on both ends of it. All right, lost my train of thought right there. The growth hormone from the pituitary gland is acting on the epiphyseal plate. And it is actually acting on both sides. It is going to cause the epiphysis side to grow more cartilage. Remember, that grows us in length. And it's going to cause the diaphysis side to turn the cartilage into bone, to ossify. And that's going to make sure we're not just getting a longer bone made of cartilage. All right? Diaphysis is growing longer, and the epiphyseal plate is continuing to be there, which means growth can keep on happening. All right. Two situations where the pituitary gland is not working properly. If you're not making your growth hormone, well, then that can result in pituitary dwarfism, like this actor right here. If you're making a ton of it, well, that can result in pituitary gigantism, like this former NBA player here. Okay, cool. Let's talk about other hormones that impact the growth of our long bone. Two hormones we got to discuss are the sex hormones. Estrogen, which of course is made by the ovaries, and testosterone, which is made by the testes. Now, these two hormones, of course, increase greatly in their production during and around puberty. So during and around puberty, we're going to get a lot more of these two hormones. They are also going to act on the epiphyseal plate. But they're going to act faster on the diaphysis side. This is important. So if I drew the epiphysis of a long bone, I drew a little bit of diaphysis right there. There's a little diaphysis. And I draw my epiphyseal plate. Here it is, right here. There's the epiphyseal plate. Not really the right spot, but I don't care. Should be higher up. It's all right, though. So what's going to happen is the sex hormones are going to act really powerfully right here. They're also going to act less powerfully right here. So we're making the plate turn into bone faster than we're making new cartilage. So there's going to be a growth in length because we're making new cartilage. But because we're making the bone conversion faster, we are going to have the plate get smaller and smaller. And then the plate eventually is gone. We've turned all the bone into all the cartilage into bone, and the plate is no more, and long bone length growth is done. So here is a plate that still exists, still open, and now over here it is closed. We can see these guys as well. Dun-da-da, dun-da-da. All right. Which of these hormones is going to be more powerful? Well, it's definitely estrogen. Now, you might think to yourself, well, wait a minute, boys tend to be taller eventually. How come you're saying estrogen is more powerful? Well, if you look at boys and girls who are of a pubescent age, the girls tend to grow and sort of tower over the boys. And so they tend to grow quicker, but then they also tend to stop because estrogen being more powerful is going to close this epiphyseal plate faster. In boys, the epiphyseal plate sticks around for longer because testosterone is not as powerful. And so because the growth plate sticks around for longer, growth occurs for longer, and boys generally end up being taller. All right. Yeah. Okay. Let's talk a little bit. Looks like we got a digression here. Back in the day, there were singers. There were singers called the Castrati. They're often sang in a variety of operatic performances. And of course, a castrati is the plural for people who have been castrated. So, this is terrible, by the way, the story I'm telling you here. There would be boys, and they would be castrated before puberty in an effort to stop the testosterone that would come from the testes from affecting their larynx and changing their voice. So these boys would grow up, and they would grow taller and bigger, but their voice would stay at this high pitch, which was a desirable thing for people at this time. Yeah, I know, this is terrible. Terrible. But here's the funny story. Not the funny story, the interesting part here. These castrati, these boys who were castrated before they went through puberty, they usually ended up being really, really tall. They ended up being really, really tall. Question is, why did they end up being really, really tall? why did Castrati end up being really, really tall? So remember, their testicles were removed, and this is pre-puberty, in an effort to maintain their high-pitched voice, so the larynx didn't have to have a chance to change. That's one of the things testosterone does. And my question for you is why they ended up so tall. So if you can figure out the answer, then go ahead and send me your answer. This is an extra credit question. Do not just copy and paste something from a Google search. Might not be right. Sometimes people just copy random stuff they find and they send it to me, and it's like, no, that's not at all what I asked for. So write this stuff in your own words. Why were these guys so tall? All right, awesome. Let's keep going, guys. Let's see if we can finish out this video. Hey, there's more growth. There's also growth in width, growth in thickness. This kind of growth is what you might still be doing to your bone. When you're doing bone remodeling, for example, this is called appositional growth. Now, appositional growth happens when you stress the bone. You stress the bone. Osteocytes measure the stress. Then they communicate with osteoblasts and clasts to remove or resorb bone in certain places and then add bone in other places, and you are going to then have growth. Bone can grow in thickness. It can remodel. This is called appositional growth. Some things that are going to stimulate appositional growth. The basic thing is stress on bone. One good way to build strong bones is to lift weights. Strength train. When you do that, you are going to increase the stress on bone. Bone is going to respond by growing in thickness. Braces. If any of you have braces or had braces, I had braces back in the day. Braces are going to remodel the bony structure of your maxillae and your mandible. If you are lifting weights and you have braces, that's even better. That's even more appositional growth. Okay. Let's define some terms too. In terms of breaking and making bone. When you are breaking down bone is known as osteolysis. Remember, lysis is the word that we use for cells bursting. So saying breaking, osteolysis, bone breaking. If you become an astronaut, one of my favorite astronauts right here, this guy. Everybody's got a favorite astronaut, right? And if you're in the International Space Station like Commander Chris Hadfield here, you are going to do some bone breakdown because you do not have the stress of gravity upon your bones like you do on the surface of the Earth. All right. The building of bone is known as osteogenesis. This young lady looks like she is doing some hang dumbbell cleans, and she is going to be stimulating bone growth. She's stressing bone, stimulates bone growth. That's osteogenesis. Of course, the dominant cell in osteolysis is the osteoclast. The dominant cell in osteogenesis is the osteoblast. All right. Now, whether you're doing osteogenesis or osteolysis, like I said, depends on the stresses you're putting on the bone, but that's not it. There's another big factor that influences whether you're breaking or making bone, and that other factor is blood calcium levels. Remember, the bone is our warehouse, our reservoir for calcium. If your blood calcium drops, that can be bad. You need blood calcium for vital things. Blood clotting, muscle contraction, nerve signals. All of those depend on proper blood calcium levels. So, If blood calcium drops, there are these little glands in your neck. All right, quick neck anatomy here. Hyoid bone's right there. We met him in lab. Below the hyoid bone, we got our larynx. Big part of the larynx right here. On the larynx is a butterfly-shaped gland called the thyroid. If we spin this around, embedded in the thyroid gland are 1, 2, 3, 4, usually 4, parathyroid glands. Parathyroid glands, in response to the drop in blood calcium, they are going to release parathyroid hormone, which I have abbreviated PTH. Parathyroid hormone is going to increase the activity of osteoclasts. There we go. And they're going to start to break down bone matrix. That, of course, is bone resorption. And if you break down bone matrix, you are releasing calcium into the blood. So blood calcium goes up. And that's not all. That same hormone, PTH, is acting on multiple fronts. It acts on the intestines to increase the absorption of calcium from your diet, and acts on your kidneys to decrease the amount of calcium you're peeing away. And this trio of things is going to increase your blood calcium. PTH is going to increase your blood calcium level. Classic negative feedback right here, right? Good old-fashioned homeostasis. It's what we like to see. But there's also the flip side to this. What if your calcium levels went up? Calcium levels that are too high can also mess with muscle contractions. So, what happens now is in the butterfly here, the thyroid gland, there are cells called C cells. Not a very imaginative name right there. The C cells are going to release a hormone called calcitonin. I like to remember that calcitonin tones down your calcium levels. Calcitonin is going to decrease your osteoclasts. So less bone resorption. Therefore, you're going to be doing more bone deposition. Plus, calcitonin makes you pee away more calcium. These two guys are going to act to reduce blood calcium levels. And homeostasis is going to be maintained. All right, guys, we are almost done. It's our last slide, actually. Few other things, few vitamins that are essential for bone homeostasis. You need vitamin. What vitamin am I hinting at with this picture of the delicious fruits? That, of course, is vitamin C. Maybe you recognize its chemical structure right there. Vitamin D is down here, hence the sunshine. You need vitamin D and vitamin C. Vitamin D is for proper calcium balance. You don't absorb enough calcium without vitamin D. Vitamin C is necessary for collagen synthesis. So, if you want strong bones, you need vitamin D and vitamin C. You should be in the sun, okay? Be in the sunshine, drinking a smoothie rich in vitamin C and D. So make yourself a smoothie, make it with some milk. You got calcium and vitamin D there. Stick some salmon in that smoothie, rich in vitamin D as well. Then stick a kiwi in there, stir the whole thing in there. A papaya, strawberries I think are rich in vitamin C as well. So put all that in a blender. Maybe add a little ice to it. Mix it all up. Drink it outside to get that UV radiation. And then meanwhile, you're out there, you're drinking your smoothie. Hopefully you're lifting weights outside as well, because that's stress and bone as well. That's your recipe for strong bone right there. All right. I think we're done. Please don't actually make that smoothie. I absolve myself of any responsibility if you do. Make it and drink it. All right, guys, we're done with the bone tissue lecture. Awesome and fantastic. I will see you next time. Bye bye.